Okay, as promised in the last video, we're going to go ahead and take a look at the rest of the examples in this section of the notes. This next problem wants us to sketch a heating curve for bromine using the following information. So what we need to do is we need to make a y-axis and an x-axis. And as we do that, we can then make our little area right here, which is going to be for a solid, and then the plateau where the phase change occurs. And then go ahead and rise again here in my liquid area, and then another plateau for a phase change. And then I get into my gas section. So now I also need to be sure I include my melting point and my boiling point. And it tells me right here that my melting point, my T sub M, is -7 degrees Celsius. And it also tells me that my boiling point is 59 degrees Celsius. So as long as we know that this is our temperature and this is our energy, then we are good to go as far as making this a proper um, energy diagram. Okay, so now we want to go ahead and take a look at this next example. So let's go ahead and we'll get this erased. And let's take a look at part 1 here. Part 1 tells us that it says calculate the energy change for 125 kilograms of liquid bromine when the temperature is changed from 55 degrees Celsius to -7 degrees Celsius. So let's go ahead and take a look and see what we can do. So this tells me that we are changing the temperature. Okay, we're changing the temperature of liquid bromine. So on our little chart, we are right here in this area because we're at a liquid bromine, but we're not changing phase. So I know that since I'm changing my temperature, I'm going to use my MCAT formula, which is delta H equals MC delta T. Well, my mass is 125 kilograms. I know that according to my formula, though, I have to make sure that that's in grams. So I'm going to do 125,000 grams times my specific heat capacity, which is 0.23, times my delta T, which is -7. That's my final temperature. -7 minus 55. And so now I can plug all this into my calculator. And so I get 125,000 times 0.23. And then I'm going to do open parentheses, -7 minus 55, close parentheses, and hit enter. And that's not quite what I'm wanting. -62 times 28750. And so I end up getting 1.78, -1.78 times 10 to the 1, 2, 3, 4, 5, to the 6th power. Okay, and of course this is in joules because my unit for specific heat is in joules. So let's go ahead and now we'll take a look at part 2 down here. This wants us to determine the energy change when 33.8 grams of liquid bromine is frozen at -7 degrees Celsius. Well, here, now we're freezing, and so now I'm going from liquid bromine to solid bromine. So now I'm right here at this plateau, which I kept in class calling area number 2, okay? So what we're going to do now is we're going to use our heat of fusion formula, which is delta H equals our moles times our heat of fusion constant. So to get our number of moles, I'm going to do 33.88 divided by the molar mass. Remember, bromine is diatomic, so the molar mass is 159.8 times the heat of fusion, which is 10.57. Now, this goes into my calculator, 33.88 divided by 159.8, hit enter, and now I can multiply that number by 10.57, and I get an answer of 2.24 kilojoules. The reason I know that this is kilojoules is because right here it gives me kilojoules. Now, for this last problem here, what we would need to do is, let me go ahead and erase this. There we go. Okay, so for this last problem here, it tells me to determine the total energy change when liquid bromine at 55 degrees Celsius is changed to solid bromine at -7 degrees Celsius. You have to be very careful the way you read this problem. So if I'm looking back at my chart, okay, I'm starting with liquid bromine at 55 degrees Celsius, okay, so that's going to be somewhere around right here, and then I'm freezing it, okay, I'm going all the way to solid bromine at -7 degrees Celsius, which is right here. So I now have two parts of my graph which are being encompassed. So that means I have to do two formulas. So I'm going to do an MCAT formula, delta H equals MC delta T. My mass from back from my, let's see here, use your steps from above to help you. So let's go ahead and do the one that was 125,000 grams. We'll go ahead and, or 125 kilograms. That's the one we'll use. So my mass then is 125,000 grams. We're going to multiply that by the specific heat, which was 0.23. And then we're going to multiply that by our change, which was our final temperature of -7. And it's still -7 because even if it's right here, even if we're doing this distance from here to here, it's still going to -7 degrees Celsius. Okay, so that'd be -7 minus our initial temperature of 55. So now I type this into my calculator. I've already done it. I believe the answer that we got was 1.78. I've already lost it. I believe that was 1.78 times 10 to the 6th joules. Okay, so that is the first part of our answer. Now I also have to go from here to here using my delta H equals heat of fusion formula. Equals moles times heat of fusion. And I know that my heat of fusion from back here is 10.57. My number of moles would be 125,000 divided by the molar mass. The molar mass was 159.8. And I can put all that in parentheses. And so now I'm going to go ahead and plug this number into my calculator. 125,000 divided by 159.8 equals, multiply that number by 10.57, and I get 8,270 kilojoules, because right here I have kilojoules in my heat of fusion constant. So now I need to convert one of these to either kilojoules or to joules. So I'm going to go ahead and convert my joules to kilojoules. So that means that when I convert this, I'm going to end up with 1,780 kilojoules. Let me make sure of my math real quick. 1.78 times, or excuse me, second E 6 divided by 1,000. Yes, 1,780 kilojoules. And so now it's as simple as just adding these two values together. And so when I add those two values, I get plus 8,270. I get 10,050 equals 10,050 kilojoules. So the amount of energy that it takes to get from here to here would be 1,050 kilojoules.